Good evening. Okay. Maybe we can wait a couple of minutes if more people will join. And we can get started after that. Or maybe in the last week when we discussed about circular TDMA, like I didn't go through the algebra part of it, so I just uploaded this notes on that so that you can go through the algebra. I hope you went through it, otherwise you can go through it. Uploaded in the same folder of the last week's lectures, like in the week 5 folder I uploaded this particular notes. So like if you just go through it, the main point is in the only difference between the normal TDMA versus this when you have a periodic boundary condition is this particular step, where in the normal one you would just have phi expressed as but now in addition to this constant term you also have a phi n minus 1 term. So you can go through this math and let me know if you have any doubts, or if you have time in the end of the session we can go through the derivation once. Yeah, I think we can get started. I hope I am audible now.
Yes, you are.
Yeah, thank you. Yeah, so the question is again a standard one. So you have a steady state conduction equation with a constant source term, and it's their Dirichlet conditions. At both you have at x equal to 0 as well as at x equal to 1 you have 0 conditions. So you have to solve using Gauss-Seidel TDMA, and then you need to determine the flux at the boundaries. So you have at x equal to 0 and at x equal to 1, and it is also given k equal to 1 and s is also equals to 1. So you just have the normal equation. This is pretty straightforward to solve, so we will just consider two cases. Like we have been discussing previously, like this is our domain. We can discretize in two different ways. So it asks about with 4 cells. So you have 4 cells. So this particular kind of discretization will ensure that your boundaries lie on this face, where the face centers will be lying on the boundaries. Alternatively, you can choose this as your cell centroid, and this is your first face. So this is exactly like you will be only considering the half cell in the domain. can take even more phases. So this is just a half cell. This is another half cell. These are your cell centroids. This is my 0, no, 1, 2, and this is my fourth one. So if you consider, say this is approach 1 and approach 2, like we have been discussing previously, like for Dirichlet type of conditions, since you need to know the phase centroid values, it will be better if you take this way. If you follow the approach 2, these nodes 0 and 4 are actually your you already know the values of T0 and T4, which are your boundary conditions. So approach 2 is not that suitable if you were to do in this particular problem, but we will see another problem in today's session where this kind of approach is much better compared to approach 1. So for now, for this, I think by now you should be familiar with these equations. So if I were to write for cell 0, the equations are, maybe I'll write for one cell. So this is my cell 0. West face, and this is my east face. So we have dt dx on the east face minus dt dx on the west face plus integral west to east dx equals 0. So on the east face, this is my next cell centroid, so we approximate it as T1 minus T0 delta x, minus on the west face T0 minus the boundary condition is taken as 0 by, you just have the half width here, so that is delta x over 2, plus this you are approximating with the mean value. So the first equation is similarly for cell 1, the equation will be T1 will be in terms of T0 and T2 and some constant. So since it is an interior cell, so you have contribution 1 from each, so 1 into T0, 1 into T1, and then you have a source term delta x square. Similarly cell 2, T2 will be in terms of T1, T3 and a source term, so this will be 1, 1, and then you have a delta x square. Now for cell 3, again you have T3 in terms of there is nothing on the right hand side, so 0 times, you don't have anything here, and then you have contribution from the left cell, that is west cell, T2, and then some source term. But here depending on your Dirichlet condition, similar to this one, you will be having 3 times T3, and then you have a source term delta x square, and then you also have your Dirichlet condition. So here in this particular problem, your Dirichlet condition is 0, so both on the left and the right boundaries will be similar equations, so you don't have any term here. So these are my set of equations. Now we have to solve them using Gauss-Seidel method. So it is from x equal to 0 to 1, so the delta x, if it is since it is a uniform one, delta x is essentially 0.25. So what do you start with? Just take the iteration number T0, T3. Initially you just take, say everywhere is 0, for the first iteration T0 is given by, let me write equations, T0 is given by T1 plus delta x is 0.25, T1 is T2 is very similar to T1, and T3 T0 is given by, first you take expression for this. So for T0 you have contribution from T1, so this goes here, so that will give you 1625 divided by 3, it's around 0.208. And for T1 you have contributions from both T2 as well as T0, so if you use the expression for that, you have T0 0.208 plus T2 is 0 plus 0.625 divided by 2, some 0.416, and then T2, to update T2 we need value from T1 and T3, so T3 goes here, T1 also goes, so if you substitute the values, T1 0.416 plus T3 is 0 plus 0.625 divided by 2, and for T3 we just have contribution from T2, that gives us T2 plus 0.625 over 3. So this is for iteration 1. So if you do it again, I think procedure is again the similar. So you just take T1 plus 0.625 and then T1 is in terms of T0 0.347. So if you observe, like each time we are taking the latest value that is available. So even here when you want to update T0, you will be taking the value from here. To update T1 we will use T2 and the latest value of T0 and the latest value of T2, both the latest values. The latest available value of T2 is 0.521 and the latest available value of T0 is 0.347. So 0.347 plus T2 is 0.521 plus we have a 0.625 divided by 2.
Sir,
Yeah.
question actually.
Yeah.
So if you have time dependent equations, I think it will be very much similar to this if I'm not wrong, the equation solved. So
You will be solving only for particular time step.
Yes, so in that case I don't think you will be using the latest values, right? You'll be using the previous values only to update the any values.
It depends on the scheme you are using. Like if you are using a purely explicit scheme, then you will be using only the whatever values are there previously. But if you have to use some implicit scheme where, so you mean the latest iteration in the sense of time, right?
Yeah.
So in the time you can use an implicit method, right?
Say that our say that we are trying to find values T0 rather than iteration. Let us say that 1 is time step, 2 is 2 dt, 3 is 3 dt.
Okay.
We are moving like that, and we are solving for T0 or T1 at 2 dt. Okay. Will you be using T0 at 2 dt to compute T1, or will you be using will you be using the iteration of first iteration to find the T1 value, or you understand what I'm trying to?
No, I didn't actually get it clearly. So you are saying, so this is 0,
No,
this is essentially dt, this is 2 dt, is that what you are saying?
Correct.
Okay, so if it is something like this.
Second one is 2 dt.
Okay,
second
fine.
is 2 dt, first dt, yeah.
Okay, so it's something like this, then?
Yeah, so that, so at T2, at 3 dt.
At 3 dt?
Can you just circle out down next T2 can you down
this one?
So you want now at T2. So I'm trying to find the value of T2 at 3 dt. Okay.
T2 at t dt. Okay. You mean to say this value? Okay.
Yeah, exactly. It's, at 3 dt, because we already computed T0 and T1 at 3 dt.
Okay.
So will you be using T1 at 3 dt, or will you use T1 at 2 dt to compute this value while you are actually marching in time?
If it is marching in time, okay, then it is actually slightly different. Then it depends on your scheme, right? Okay.
Of course.
You are familiar with FDM, so you might be aware of implicit and explicit schemes. Or if not, maybe we'll take it up at the end of the class. So end of these questions. So we will take it up in the end.
Because you're using values at previous time. Of course, it is kind of related to the current class as well. I just wondered. Yeah, in FPM, I think we'll take the values in the current time and we'll solve for all those values
in the previous one.
Yeah, actually.
So it's kind of an implicit scheme. We will. I mean, I'll take like the last problem is essentially that. So we will discuss that.
Okay, you can just iterate this and get the answer.
Yeah.
Possibly.
Yeah, I just want to take 2 iterations to show you one thing.
Okay, sure.
So where is T? So we are T2. You get from values of T1 and T3. So 0.746 plus 382 plus 625. And then finally T3 is 0.876 plus 0.625 over 3. This particular problem we already know the solution, so since it is d square t by dx square plus 1 equal to 0 and both the ends are essentially we are keeping it 0, what we expect is some profile like this where you have maximum somewhere in between. Since it's symmetric problem, so you have maximum at the middle, say x equal to 0.5. So if you observe even in all these iterations, what is happening is something like that. You start somewhere here and then it goes on to the other end. But what misses out here is the symmetry. So how do you get the symmetry? It's like by the nature of the problem it has to be symmetric, right? If you see the original problem, this is x equal to 0, this is x equal to 1. At both these values you have t equal to 0, and if it is a steady state conduction with a uniform source throughout, and because of Dirichlet conditions, what happens is you you have both the ends at the same temperature and then you have a source in between, so you need to have a maximum temperature at the center. So as you iterate, what you expect is your profile initially starting with the constant 1 should gradually reach this, like it will keep on going like this, and finally it will reach something like this, like this is the final solution. So instead, if you have a different boundary condition, say if this is t equal to 0 and this is t equal to 1, so when you start out you might have 0 everywhere. This is our initial guess. So what will happen, just after first iteration you will have something like this, and then it keeps on going till you, like depending on the source, it keeps on going to the final state. So what always is happening is something like this. So you have information moving from the boundaries towards your interior. In case of t equal to 1, this particular value of 1 will keep on propagating inside. So initially only the near boundary values will be closer to 1, and after the next iteration the nearby values will keep increasing, and if you go one more step further, the other values will also keep increasing. So as you go iteration by iteration, these values will keep on increasing, trying to balance this out. So this is something what we were discussing even like if you have something like for convergence criteria, we were discussing if you have Dirichlet condition, your convergence is kind of assured because this is something how the information will propagate. But when you have Neumann type of conditions, you don't have this information. You just say the flux is 0, so information doesn't come anything to that. So unless you specify the temperature or some reference, only then this information will propagate inside and your iterations will kind of converge. Or maybe if you can try later maybe with different boundary conditions. So make this boundary condition as t equal to 1, and then you can see how the iterations will proceed. Maybe I will show it in the code, so you can see how the iterations will go and the values will converge. It will be something like the t0, it will be something like this. So initially everything will be 0, and these values at the end will keep on increasing, and finally they will reach a steady state. Now if you were to use the same method using TDMA, solve the same problem using TDMA, so these are my equations. Okay, these are my equations, so we will start with this. So I have to solve this using TDMA. How do I proceed? So in TDMA, the first step is the general form of equations is AI TI equals BI TA plus 1 plus CI TA minus 1 plus DI. So in our particular case, we just have 4 equations. So this is AI, BI, CI and DI. Initially, we have for I equal to 0, AI and for I equal to 1, 2 and 3. B is essentially the coefficient for t plus 1. So we won't be having for the last cell. Ci is for the next one. So we have this. And di is for the remaining constant term. So if you recall the algorithm, the first step is you get the values of Pi and Qi. In the forward iteration, you have to constantly iterate this value. So we define P0 by B0 by A0, Q0 by C0 by A0. So if you do that here, so this is D0 by A0. So Pi is 1 by 3 and Qi is so how do you update the values? What is the value of Pi in terms of Pi minus 1? And Qi is given by Ci Qi minus 1 plus Di by AI minus Ci Pa minus 1. So I know the values of P0 and Q0. So P1 is essentially B1 by A1 minus C1 into P0 and Q1. Okay, first we may calculate this one. So P1 is essentially B1 is 1 over minus C1 into P0. So this is around 0.6 and Q1 is C1 into Qi minus 1 is 5 over 24 plus D1 is 0.625 by 2 minus 1 by 3. That gives you some 0.5. Now similarly you do for the next step. So P2, use the same formula. P2 is B2 is 1 by A2 minus C2 into P1. P1 we have a value of 0.6. So this gives us and similarly Q2 is given by C2 into Q1 plus D2 by A2 minus C2 into P1. P1 is we have a value of 0.6. And similarly for the last one, you have P3 is B3 is essentially for the last one, B3 is 0. So your P3 will be 0 and your Q3 will be C3 times Q2 plus you have a d2 of 0.625 by a3 minus c3 into pi minus 1 is p2. So once we do the forward iteration, what we do is essentially this last value of Q is equal to your phi. So now we keep on updating the values of our temperature. So now we determine Ti. So we do from, so initially we went from top to bottom, now we'll go from bottom to top. So for the last one, T is equal to Q. So this will be 0.625, and then we do the normal iteration. So for the last one we have T3 equal to Q3, and for all the remaining ones we use the recurrence relation Ti equals Pi Ti plus 1 plus Qi. So T2 will be P2 times T3 plus Q2. So we just do that. So we have P2 times T3 plus you have Q2 and then similarly your T1 will be in terms of T1 will be P1 times T2 plus Q1, so 0.6 times plus Q1 and T0 will be in terms of T1 P0 T1 plus Q0 P0 is 1 by 3 Q0 5 by 24. So once you go from the reverse directions, you get all the values of Ti's. So now we have the values of Ti. The next is essentially to calculate the flux at the boundaries. So we have this as our domain. This is x equal to 0, x equal to 1, and then I have divided it into 4 cells. So this is my T0, T1, T2 and T3. So on the west boundary, your flux is given by K is essentially 1, dt dx on the west boundary, like we have approximated it as minus T west boundary by delta x over 2. T0 we have the value by and similarly on the east boundary So next question essentially asks you to okay, so this is something we discussed in terms of periodic boundary condition in the last week. So you have this is x equal to 0 and this is x equal to 1. Now what we are saying, we are rolling this up into something like this. So this is my 0. So I'm dividing it into phases. So put the nodes here, 1, 2, 3. If these are my nodes, 1, 2 will be here, and 3 will essentially coincide with the 0 node. So this is how you will be getting. So in this particular case, how will we write the equations? It's like it's the similar equations, everything is straightforward. So we just take the same old equations. So we have 3t0. So if you just take the same old equations, these are the old equations. Now the only difference is, now when you are writing for this, previously we didn't have any ti minus 1 term, so we have taken the fluxes at these boundaries, but now we have to write in terms of phi n minus. So your ti minus 1 term, previously whatever we were having, now will be replaced with for the boundary for I equal to 0, ti minus 1 will be replaced with t2, and for I equal to 2, ti plus 1 will be replaced with t0. That is going to be the only difference. So what will my equations be now? So if we take for this particular case, this is one portion, this is second portion. So this is one portion, this is another portion, okay. This is another portion. We'll call them 1, 2, 3. So this is 1, this is 2 and 3. So if I'm writing the equation for 1, how will it be? So on the east face we'll be having t2 minus t1 by delta x. On the west face it will be t1 minus t0 by delta x, plus we have a source term equals 0. So this will give me 2 times t1 t0 plus t2 plus delta x square. Similarly for the second region, if we write the equations, on the east face we have t3 which is equal to t0 minus t2 by delta x minus delta x, plus you have a source term. This gives us 2t2 equals t0 plus t1 plus delta x square. Now similarly for region 3 on the east in the sense, if you go in the so I'm just considering, like if you go in this direction, whatever comes down the forward positive direction I'm considering as east, and on the other direction I'm considering it as west. Like it's just a notation, you can follow whatever way you want. So for the third region on the east we have t1 minus t0 by delta x, minus towards the west side we have t0 minus t2 by delta x, plus the source term. So this gives us 2 times t0 in terms of t1, t2 and delta x square. So now I have 3 equations. So essentially I have 3 equations and 3 unknowns. But you can see, like previously when we were having Dirichlet type of condition, we have some known values from which the information is flowing into our system, but here we don't have anything like that. Like physically or maybe you can try seeing the rank of this matrix, the rank of this system of equations, which will be less than 3, or even simpler, you can just add these equations to see if their like one equation is actually dependent on the other two equations. So you cannot get a unique solution with this system of equations. So to get a unique solution, like we have discussed previously, we need to fix one of these values. So if we fix t0 to be 0, then we will get some values for t1 and t2. So if we fix t0 to be 0, then we have the equations as we will take the second two equations. So 2t1 will be t2 plus 0.625, and then 2t2 equals t1 plus 0.625. You can see, like from this two equations, like t1 equals t2, which gives us 0.625. So like we do not fix any of these values for t0, then we won't get any unique solution. So we need to fix one reference value and then get other values in terms of that reference value. I think this is clear. We discussed this last week. If you were to compare these solutions, the values of t1 and t2, okay, circular TDMA we cannot compare, but if you solve this Gauss-Seidel method and from TDMA, you would be getting the same values if you iterate. I just stopped at third iteration, but if you see, the values will keep on increasing. So iterate like around, it converged after like 7 or 8 iterations. After you do 8 iterations, the values will be converged to this, will converge to these particular values. The second one is also a straightforward question, but the only difference is now you have a 2D domain. So instead of the east and west cells, now you will be having east, west, north and south cells. So you will be having all the 4 coefficients that you need to find. So it asks you to do along 3 cells along x and y directions. So we have a domain something like this. If I split it into 3, this is my x and this is my y. So here you have values as 0, 0, and along y you have values of 1 and 1. Just these are my cell centroids, and say I am naming as 1, 2. Just giving some numbers. So yeah, by now I think you are familiar with the notation. So what do you think the equation for cell 1 will be for this particular cell number 1? T1 will be in terms of, you will have T2, okay, maybe I should write the equation also. The governing equation is d square t, dou square t by dou x square plus dou square t by dou y square, plus I think you also have a source term, plus 1 equals 0. So if this is my governing equation, boundary conditions are as shown. For cell 1, it will be in terms of neighbors. So you have T2 as a neighbor, T6 as a neighbor. So what are the coefficients? Can one of you solve and maybe we will see. So we just take delta x to be 1 and delta y to be 1 just for simplicity. So what will be the coefficient of T1, T2 and T6? T2 coefficients will be in terms of delta y and delta x. So here we have just 1. So here you have a 1, here you have a 1, and since the source term doesn't have any contribution from the gradient, so your AP will be summation of these two values. So you have 1 plus 1, so you have a summation of 2, but then you have the half cells here. So you are getting a 2 from T1 and T6, and then you have a half coming from the other two borders. This will be this, plus you have a source term. Source term is essentially 1 here. You just have 1. I hope it is clear, otherwise we can do for one cell at least. So if we'll do for cell 1. For cell 1, the equation will be del T del X on the east face, west face, similarly del T del Y, north minus on the south face, plus you have a source term, that is 1 into delta x delta y, which I am considering as 1, delta x equal to 1 and delta y equal to 1 equal to 0. So on the east face you have T2 minus T1 where delta x is 1. On the west face you have T1 minus the other value is 0 by delta x by 2, it is just a half cell, plus on the north side you have T6 minus T1 by 1 minus on the south face you have T1 minus the boundary condition is 1 by 1 over 2 plus now if you see the coefficients, we will take 1 to the other side. So T1 will be in terms of T2, T6 and some constant terms. So the coefficient of T2 is only from this equation, this term, so that is a value of 1. Coefficient of T6 will be only from one term, that has a value of 1. Now coefficient of T1 will be 1 from T2, 1 from T6, and then you have two boundaries, so that is over half and half. So you have 2 plus 4, and then on the source terms you have 1 coming from the source and another 2 coming from the boundary term, the south boundary. So you have this. So now the equation is 6 times T1 will be T2 plus T6 plus 3. Similarly you can write for T2 so now if you see for T2 second cell you have 3 neighbors and then one boundary. So the 3 neighbors will be like you have T1 plus T3 plus T5. So what are the coefficients? The coefficients will be similar in every direction, only for the boundaries is where you get different coefficients. So for cell 2 on each of these coefficients will be 1. So now you have 3 coefficients, like you always see AP is sigma A and B plus some additional terms. These additional terms can be because of source. When you have a source term you have a minus SP term, and then you also have some boundary terms when you have some boundary conditions. Essentially if you have a Dirichlet condition you will have a half over here, but if you have a Neumann condition you do not have any term here. So your T2 will have, now you have 3 neighbors, so sigma A and B will give you 3, and you have one boundary. For each boundary you will have a 2 coming up, so you have 2 over here. So this is 5 times T2. And coming to the constant terms, the boundary here is a south boundary, so you have because of Dirichlet condition you have a 2, and because of the normal source term you have another 1, so this comes up to 3. Now similarly for T3 you have only 2 neighbors, T2 and T4. Now the neighbors will have coefficients 1. Now for T3 it will be sigma A and B, so you have 1 plus 1 2, plus you have two boundaries, so that will contribute to a 4, so 2 plus 4 will give you a 6. And then you have a constant term. The constant term you have one boundary, so it is very similar to cell 1, so you just have the same coefficient here. So now for T4 it is very similar to, you have for the fourth cell you have 3 neighbors, cell 3, 5 and 9. So you have T3, T5, T9, so all of them will have coefficients as 1, and you have one boundary towards the east side. So you have 3 plus one boundary will give you 2, so this is 5 times T4. Now you have one boundary, but that boundary has the value of 0. Since it is only one boundary and the value is 0, you won't have any source term adding up. It will be just a value of 1. Now for the fifth cell, T5 will be in terms of 2, 4, 6 and 8. It will be T2, T4, T6, T8. It doesn't have any boundary cells, just has the source term, and it's sigma AP equal to sigma A and B, so you have 4 coefficients, so you just get a 4 here. T6 will be in terms of 1, 5 and 7. So all of them get a coefficient of 1, and it has one boundary towards the west side, and that value is 0, so it doesn't have any contribution to the source term, but your AP term will get contribution from that. So you have 3 plus 1 boundary term, so 3 plus 2 will give you a value of 5. So 7 has 2 boundaries, 6 and 8, and one of them has a value of 1 on the top. So you have 1 coming from the source term and 2 coming from the boundary term. Similarly here 2 plus you have for the 7th cell you have 2 boundaries, one on the west and one on the north, so you have 6 here. So T8 has 3 neighboring cells, 7, 5 and 9. The one on the top has a Dirichlet value of 1, so that will contribute to your source term. Here you have 3 plus 2, 5, and T9 is again straightforward, so you just have 2 cells. And you have 2 boundary conditions, so you have 2 plus 4, that is 6, and then 1 plus 2, that is 3. So now you have all the equations. So Gauss-Seidel is again straightforward, you just implement, you start with an initial guess of 0 everywhere, and then you keep on iterating this one. So maybe we will see TDMA. Yeah. I think Gauss-Seidel is straightforward for you to implement in this, so maybe I should ask the question directly. Can I implement TDMA in this directly? Can I solve it using the TDMA?
We use line by line TDMA, right?
Yeah. So why is it that I can't use TDMA directly here?
Because in normal TDMA, we relate the TI with TI plus 1 and TI minus 1. Here we have J terms.
Here we J terms. So essentially you need only 2 unknowns, but here you have some equations which have 3 and 4 kind of things. Yeah. So you will not be able to solve directly using the TDMA. So we have to use the line by line TDMA. So maybe we will do only one iteration of it. So how do you proceed with the line by line TDMA? So we fix along one direction, and we take Gauss-Seidel along one direction and TDMA along the other direction. So say suppose we will take Gauss-Seidel along x and TDMA along y. So if this is our direction, if we follow this particular way, so you have so if we follow that and we take the initial guess everywhere as 0, so if t for all the cells I am just taking as 0 as the initial guess, so I am taking along the y direction as my TDMA. So I have 3 equations. So the first, if we take along this line, so what is the equation for T1? We have 6T1 equals T2. T2 is not along that particular line, so we take the value of the initial guess into that value. So the original equation is T2 plus T6 plus 3, but instead of this equation, what we will be doing in Gauss-Seidel, yeah, someone had raised a hand. Yeah, you can ask. Yeah, you can ask. I'm not able to hear if you are asking something. You have some question? Or yeah, maybe you can type in the chat box. I'm not able to hear if you say anything. I guess it's maybe by mistake. Okay, so how do we start? So along only that particular line we will be taking as unknown, and all other variables will take the values of the guess, the initial guess. So when we have assumed initially everywhere to be 0, so along this particular line our value of T2 is something that is not lying on the line, so we will take the assumed value of that. So this equation becomes 6T1 equals T6 plus 3. Similarly, we have T6 equation for T6 as 5 times T6 equals T1 plus T5 plus T7 plus 1. So even in this particular equation we do not have T1 is along the line, T7 is along the line, but T5 is not on this line, so we take the assumed value for that. So now our equation becomes 5 times T6 equals T1 plus T7. The assumed value is 0, so you have 1. And then we have for cell 7, the equation is 6 times T7 equals T6 plus T8 plus 3. So even in this T6 is along the particular line we have chosen, but T8 is not along the line, so we will take the assumed value. So this becomes 6 times T7 equals T6 plus 3. So now we have these 3 equations and 3 unknowns. This can be solved using the TDMA algorithm. So we follow the same steps like before. So you have I, AI, BI, CI and DI. So you have 3, so that is 1, 6 and 7. So 1 you have this. BI is for the next one. So when I am on the cell 1, I plus 1 term is essentially the next one. So this is my I plus 1 term. So this is my I, this is my I plus 1. So it should correspond to the 6, and then CI is 0, DI is 3. Similarly you have for the second one, I plus 1 is 7, so you have a coefficient of 1, and I minus 1 is 1, DI has value of 1. And for the 7th cell you don't have I plus 1 term, the I minus 1 term is 1 and this is 3. So the process is very same. So you just start with PI, QI. You first go from top to bottom. In the top to bottom approach, P0 is given by B0 by A0. So the equations are same. And your Q0 is given by D0 by A0. So P0 is 1 over 6 and Q0 is 1 over 2. And your Pi or your P1 is written in terms of P0. So P1 will be B1 by A1 minus C1 into P0. So that gives you A1 minus C1 into P0. And similarly Q1 will be C1 Q0 plus D1 by A1 minus C1 P0. C1 times Q0 plus d1 and for the last one p will be 0, your q value will be q2 will be c2 times q1 plus d2 by a2 minus c2 into p1. So this gives you c2 times q1 plus d2 by a2 minus c2 into p1. So once you are done from the forward one, next you do the reverse. So to obtain the values of ti, you start from the last cell. The value of last one will be equal to ti. So q2 equal to t2 or t7 will be equal to q2. Now if you need the value of t6, will be in terms of p1 t7 plus q1. So that gives me 0.207 to t7 is 0.571 plus q1 and similarly for the last cell, if you need the value of t1 will be p0 times t6 plus q0. So this is 1/6 times t6 plus q0 is 0.5. So now you got only along one line. So after getting this, what you do for the next line? So if you take our original ones, now in the previous step we fixed along along this line. Now we will fix along the other one. Now we will fix along the second line. So now we take the equations for 8, 5 and 2. Now we have the equation for 8. So we need to be taking equations for 8, 5 and 2. So I am just taking along this line. Now in these equations, only the ones lying along that line we will be taking the values. So for the first equation, 5 times t2, t1 is not lying along the line, but since we are using a Gauss-Seidel method, we will take the latest value of the t1. The latest value of t1 is 0.571 instead of 0. So we will take that value 0.571 plus the latest value of t3. T3 is not updated, so we will take the initial guess. T5 is lying along the line, so T5 will remain the same, plus 3. So this gives us one equation, 5t2 equals T5 plus 3.571. Similarly for the fifth cell, we have 4 times T5, T2 is lying along the line, T4 we take the initial guess, 0, T6 we already obtained the value here, it's 0.428. And T8 is also lying on the line, so we will take T8 plus 1. So the equation will be 4 times T5 will be T2 plus T8 plus 1.428. Similarly for the last cell, T8, T7 is not lying along the line, but we should take the latest update value. The latest value is 0.571, so we take that value 0.571 plus T5 is along the line. T9 is not along the line, but we don't have an update value for that, so we take 0 plus 3. So this gives us 5 times T8 plus T5 plus 3.571. So the process is again similar. So now you have, like, we again applied the TDMA. So you have I. So if you just take this, so now we have three T2, T5 and T8. The equations are 5, 4, 5. For the 2, the next cell is 5. 5, the next one is 8, and for 8 we don't have anything next. For the first one we don't have any previous one. For T5 we have T2 as the preceding one, and T8 we have T5 as the preceding one. And the DIs are 3.571, 2.428 and 3.571. So the process is again similar. So you start with Pi and Qi. So initially P0 will be B0 by A0, Q0 will be D0 by A0. So once you get P0 and Q0, you just start with the iteration. So I think the process is clear. So P1 will be in terms of the previous ones. So you have P1. So this is 0, 1 and 2. These are the notations I am using for P and Q, and this I am using for T. So P1 will be B1 by A1 minus C1 into P0. P1 by A1 minus C1 into P0. Q1 will be C1 times Q0 plus D1 by A1 minus C1 times P0. And for the last one we don't have P, we just have the Q. So Q2 will be equals to T8, and that is equals C2 times Q1 plus D2 by A2 minus C2 times P1. So C2 times Q1 plus you have a D2 of 1 by A2 minus C2 into P1 if you go to Ti. So now that since the forward sweep is done, now we will do the reverse one. So this is equal to A35, and T5 will be P1 times T8 plus Q1 similarly T2 will be P0 times T5 plus Q0 Once you got these values again, now it's the same thing, we'll repeat the same step again. I think you got the hang of it. So in the last iteration, in the next iteration, now we are done with this line. So in the last, we will do for the last section as well. So once you do all of that, you then again repeat it. You keep on repeating this till your values, till the values of temperature, the change in the values of temperature across from one iteration to the next iteration is within your tolerance limits. I hope the method is clear. So to calculate the fluxes is again the same. So once you solve all these equations, say on the east face, so if you want to calculate flux at this point, so this is my current cell, this is my east face, so the flux will be minus k times del t del x on the east face. K is essentially 1 here, so 1 times these boundary value, we already know the value, minus Tp delta x by 2. So this is very similar to your 1D problem. The only difference is if you are calculating on the east face, you should correspondingly take that particular phase. So the flux on any phase is given by now if you want the value of the flux, you should just take the dot product with the corresponding normal vector. So on the east face, your normal vector is pointing along I cap, so this doesn't change the sign. So on the west face, it will be you will get a minus sign over there, since the normal vector will be pointing along the minus x cap direction. Now very similar to your 1D case, in 2D case, if you want to apply your circular TDMA, the boundary conditions will be like, so now in our grid, what we are saying is now we are merging this boundary with this boundary such that you essentially don't have two different cells now. So your 1, 2, 3 is now combining with your 7, 8, 9. So when I roll this up, your 1 and 7 will be same, 2 and 8 will be same, 3 and 9 will be same. You just have 6, 5 and 4. So when you write equations for that, it will be very similar to the previous case. So the only difference is now your T1 will be equal to T7, T2 will be equal to T8 and T3 equals to T9. That's the only difference between this and the normal TDMA. I guess that is clear, or if you have any queries. Please, someone raised a hand.
Can you explain the last
this one?
What is this? Yeah.
So if I were to roll this as a sheet, so you have a 2D plane. So if I am rolling this as a sheet, such that these two, the top one and so this particular one and this particular one are joining with each other. So it's
okay,
like you have a plane of paper, you then roll it as a cylinder.
Okay, got it.
The only difference is like you solve it, you just make this as this, like then you get your set of equations, right? That is your new equations. So your 3 unknowns have reduced. That's the only difference. Third question is okay. So you have d square phi by dx square plus phi square equal to 0. x equal to 1 is also 0. Okay, first this type of PDE, like we have discussed previously, so this is a nonlinear PDE. So if you were to solve it directly, naturally you will end up with some, you will not get a linear equation, you will get some nonlinear equation. So we then have to linearize this term. So comparing this with our standard form, so our standard form is something like del dot gamma del x gamma del phi plus some source term equals to 0. So if you compare this with this, you have gamma equals to 1, and then your SP is given by phi square. So how do we go ahead? Like the first question is essentially you have to linearize the source term. So how do we start with that?
We use Taylor series.
So my S is given by phi square. So what do we do? So we write it as some S of phi star plus ds d phi calculated at phi star. So we just take the first term. So this is phi star square plus 2 phi star times phi minus phi star. So this gives you minus phi star square plus 2 phi star phi. So this is my source term. If I were to discretize on how many cells? So 3 cells. So if it is, this is my domain, x equal to 0 to x equal to 1, and I am discretizing it into 3 cells. This is my cell 0, cell 1, cell 2. Say for cell 1, when I am writing the equation, so this will be my west face and this is my east face. So dt dx on the east face minus on the west face, plus you have a source term, integral west to east. You have, so if you compare this with SC plus SP phi, dx equals 0. So on the east face it will be T2 minus T1, save delta x equal to 1, minus on the west face T1 minus T0 where delta x is 1, plus here you have an SC times delta x, plus the other term we will just take the linearist form, so it will be SP times okay, it should be consistent, we are following the notation of T. So SP times T of that current particular cell. So our cell is, we are writing equation for cell 1, so that will be SP times T1 equals 0. So if you just group the terms, T1 will have 2 minus SP, T2 we don't have anything, T0 we don't have any terms, and then we have an SC term. So if we substitute the values back, what is the value of SP we have chosen? So from this equation, SC is minus phi star square and SP is 2 phi star. So you have 2 minus 2 phi 1 star. Okay, I just got, okay, I was confused with the notation. So we are following as phi instead of T. So this is T phi dx. This is T phi. This is phi. Yeah. Maybe for this one cell. So all of these are in terms of phi. Just say in terms of phi. We are writing equations in terms of phi. So we'll have phi 2 minus phi 1 minus phi 1 minus phi 0 plus SC times 1 plus SP times phi 1 times delta x equal to 0. If you just group the terms, you have phi 1 for 2 minus SP, and then you have phi 2, phi 0 and a constant term SC. So if I substitute that back, 2 minus SP is 2 times phi star 1, phi 2 plus phi 0 plus SC is minus V star square. If I write for cell, okay, maybe we'll stop here once. So for this particular case, if you try to apply the Scarborough criteria, so here you have sigma A and B is 1 plus 1, that is 2, and your AP is 2 minus 2 times V1 star. So you have sigma A and B is actually greater than AP. So what does this mean? So like, will it converge if I use an iterative method? It shouldn't converge. So what should we do now? So if we go ahead try to solve in this particular way, it will not converge. It is essentially because you have your SP term which should be actually negative, but in this particular case we have a positive SP. So since SP is positive, it will not converge in this way. So what do we do now? So we linearize in this particular way, we will not get a solution. So we have to change the way we linearize, or else we have to use some under relaxation, like as Sir will be discussing in the session. So when you use an under relaxation, you have to choose a very low value so that it will converge. But for now we will just write the equations, and then maybe we will see how it differs from different cases. So one approach is this: for cell 0 we will write equations for all the cells. For cell 0 it is again straightforward. You just have on the east face Phi1 minus Phi0, and on the west face you don't have any value. It is just a half cell, and then you have source terms. Just group the terms. For Phi0 you have 1 plus 2, 3, and then you have similarly for the last cell. For cell 2, the equation will be very same, like you have similar boundary conditions, so the equation will be similar. So Phi2 times 3 minus 2 Phi2 star will be in terms of Phi1, and then you have a constant term like this. So before solving these equations, like you have said, like if it doesn't satisfy the Scarborough criteria, so you might not get a solution. So just to show you this approach, we will go through the code once to just show you how this actually deviates. So I've just considered 3 different approaches here. Approach 1 is the one we are considering right now. So you consider using a Taylor series expansion, but then we see, like if we do it in that particular way, we might not be able to satisfy the Scarborough criteria. So what I've tried to do in approach 2 is we'll just take the normal value as the guess value. So you don't take the second term, you just consider the entire source term in your SC. You won't have an SP term. If you consider in that particular way, how will your coefficients change? Is like you just have phi square as your source term, will be going into your constant term. You just take the guess value of that. So if I compare the approach 1 with approach 2, So if I give a value of very low initial guess, say 0.1 or something, very close to the solution, then it will kind of converging after 2-3 iterations. So this is the error values. So you can see that it is converging. But if I give some higher value, say 0.5 or something, yeah. So if I actually give some higher values very far from the initial guess, then the because of it doesn't satisfy your Scarborough, then it will eventually diverge and you will not get a solution. So I'm not able to print the errors here. Maybe I'll try printing the errors so that you can see how it is actually diverging. So you see the values are keep on increasing. So I started with an initial guess of 0.5, but then the values are now around 50,000 and like that. So it just keeps on diverging and it won't converge. But if I give a very smaller value of initial guess, you can see how the values will keep. Okay, it's where it started. So it kind of started from 0.1 and then it keep on going to close to 10 power minus 7. So that is equal to 0. So that I give a tolerance of 10 power minus 6. So it converges to around 10 power minus 7. So the point I'm trying to make is essentially even when you do the Taylor series expansion, the most important thing that you have to consider is the terms you are choosing for SC and SP has to be such that SC should be positive and SP should be negative. The way you linearize should be in this particular way. After satisfying, if your Taylor series expansion doesn't satisfy this, then you have to appropriately change those things so that you can have a converged solution or use some under relaxation scheme. I think that is clear. By the way, before actually trying to compare different solutions, what do you think the actual solution will be for this equation, the analytical solution? It's like if you have both the boundary conditions as 0, so the analytical solution is phi equal to 0 over the entire domain. So when we give an initial guess of close to 0.1, it kind of converts to 10 power minus 7. So that is the value it kind of converts to. If you use either the previous one I showed you, I tried the values of both Gauss Seidel and TDNA, and that is the value it got converts to. I'll share the code in the drive so that you can try and check with other values, other initial guesses, so that you will understand what the difference will be. So the other linearization scheme, like I try to ask basically to compare with two different schemes. So the one scheme, like as you propose, you use the Taylor series expansion. The next approach is you just take the value normally. So you have SC is given by phi square. So what you do, instead of taking the second term of the Taylor series, you just take phi star. So this is your source term. So you just consider this as your SP and SP equal to 0. So if you do in that particular case for cell 1, your equation will be phi 1 and your SP is essentially 0 equals phi 0 plus phi 2 plus you have a source term of phi 1 star square. So now if you try to see the Scarborough, so your sigma A and B equals 2 and AP is also 2. So your equality is satisfied. Now when you try to check on the boundaries, you have phi 0 times, you don't have an SP term. You have phi 1 plus phi 0 star square. So here sigma A and B equals to 1 and your AP equals 3. So this satisfies your equality and this satisfies your inequality. So now your Scarborough is satisfied and then your solution will converge. So the point is, even if Taylor series you go ahead with Taylor series, but if the Scarborough is not satisfied, then you have to change your strategy in the way how you linearize your source terms. Otherwise, you might face problems with using an iterative method during for convergence issues. Is that clear? So maybe I should ask one question. So the Scarborough criteria is for convergence of an iterative method. So what do you think will happen if I use a TDMA? It's like TDMA is not an iterative method, it's a direct method. So will my choice of linearization affect the final solution using TDMA?
I don't think so. It's a direct method.
Okay. So if you have a nonlinear equation and you want to solve it using TDMA, how do we approach it is, again we use an iteration there, right? We start with an initial guess, like if you see these equations, the phi star here is actually the previous iteration value, right? It is not the current value of phi you will be using. So you start with an initial guess and then you calculate this phi star and your SC and SP. Based on this SC and SP, you solve your TDMA and then you update your phi values, and using these updated values you update your coefficients again, and with like you keep on iterating that till you get a convergence. If you are using, there are two iterations, one for the nonlinear terms. So essentially your iterations will be for two things. You have an outer loop. This is for your, that will update your phi star, and then you will have an inner loop to get the phi values from your equations, from cell equations. So what we are doing in TDMA is we are replacing this inner loop. Only this we can replace with TDMA. The outer loop still remains. So you will assume an initial value of phi star that will go into the coefficients, and TDMA will solve it, and then it will keep on going into the next one. Like the loop will, it will go from the outer loop will still be there. So you will be still iterating, but the iteration is not for the cells, but then iteration is for the phi star. So that's where you do this under relaxation and over relaxation. So by actually doing under relaxation, you will try to ensure that you will not diverge. Okay, we will go to the next question. The fourth one is essentially diffusion inside an axisymmetric condition. Okay, axisymmetric is in your cylindrical coordinates. You have an axisymmetric condition. It's just a steady state diffusion equation with a constant source term. The source term is given by QV, and you have the top and bottom walls as adiabatic, so you don't have any heat transfers. So Neumann condition, and the other sides are exposed to a fluid with a heat transfer coefficient HR, and the fluid temperature is given by T0. So how do you write the equations? So you have an axisymmetric coordinate system. So if I say this is my Z, this is my R, so this is R equal to 0 to capital R, and Z equal to 0 to capital H, and it is given like here there is no flux, so del Z is 0. On the bottom face is also adiabatic, so I have del T del Z equal to 0. On the surface, this is my surface. It says you have heat transfer coefficient. So here the heat flux is say minus K to del T del R at R equal to R is given by some heat transfer coefficient times your delta T. And for an axisymmetric case, what is the boundary condition at the center line? Is you have a symmetry, so you can either say T at R equal to 0 is finite, or because of axisymmetric condition, you just say the temperature is the maximum at the center line. So this del T with respect to R is 0. So these are my boundary conditions. So if I take any interior cell, so let's just take one cell. So this is somewhere here, so we are just taking one, we are concentrating on this each cell. This is my west face, east face, north face and south face. This is my R and this is my Z. And my governing equation is 1 by R or maybe I'll write simply as you have del dot k del t plus some source term equal to 0. So if you are writing for cell P, how you start is you just start with the Gauss divergence theorem. So you have so using Gauss divergence, this becomes k del t dot n cap dA plus since we are using linear approximation, QV will times this will be essentially QV times delta V equals 0. So when I say an axisymmetric, what we are assuming is along theta direction is just 1 radian. So my delta V is normally delta R times R delta theta times delta Z. When I am saying an axisymmetric and I just draw a simple plane like this, what I mean is delta theta is essentially 1. I am just taking unit value. So your delta V now becomes R times delta R delta Z. Now coming to this, you again take this as summation over your Ki del Ti Ai plus R I am replacing with Rp, we are taking for the value at P times delta R delta Z equals to 0. So now coming to this, we have different phases. So say on the east face, so when you are writing this term on east face, it will be K east along east direction is Kr times del T del R. So what is my east face, the area of the east face? This is my cell, this is my east face. What will be the value of AE?
Delta Z.
Delta
Z.
delta Z. Okay, so if you consider this in the way like say you have different planes, right? So in your cylindrical coordinate system, unlike Cartesian system, in a 2D Cartesian system, what we have is this will be either delta y or delta x, but now here we have, say you consider cylindricals, so this is along r cap direction. So along r cap direction, your area vector will be, you have some component corresponding to theta and some component corresponding to z. So this is what you are calling as delta z, and the term corresponding to theta, there should be one term corresponding to theta. Only if you take the element value of theta times z, you will get the area vector along r cap, right? So what I meant is, say if you want to find area along r cap, what you would be doing is something like E theta cap cross Ez cap, where these coefficients will be essentially the elemental along that particular direction. So along theta cap direction, your elemental volume, your small element will be r times delta theta, and along z direction you have a delta z. E theta cross Ez is your ER cap. So this will be your area along that particular direction. So okay, so for the east face you have, since we are considering delta theta is 1, so I am just removing delta theta. So you have r east times delta z. So now remaining will be similar. So if I just expand these terms, this sigma over here, so on the east face it will be kr times del t del r on the east face times a is r e times delta c. On the west face you have del t del r on the west face. Instead of r e, now you have r w. Now on the north face it's along z direction on the north face. So what will be the area P on the north face? So this is my P cell, this is my north face. So what will be the area of this face? So this is along z cap. So we'll have ER cap cross, sorry, theta. So here your element is delta r, here your elemental volume is r delta theta. So it will be similar. So you'll have an r north delta r, instead of delta z you will have an delta r. On the south face, and then you have a source term that is QV times RP delta r delta z equals to 0. So from here it is again straightforward. So now your del t del r, okay, maybe I should ask another question. So your RE is essentially RP plus you have, if it is a uniform grid, you have delta r by 2. And similarly R west is RP minus delta r by 2. R north is, if you are on this P cell, say since we are considering a uniform grid everywhere, all of these phase centers and cell centroids will lie along the same line. So all of them will lie along the same line, and this is my R axis. So RP and RN will be equal, and your R south face is also equal to RP, since all north face like phase centroids and cell centroids will lie on the same line. So if you substitute this, dt dr along the east face is very similar to the previous expression. So we have T east minus Tp by delta r times Re delta z, Tp minus T west delta r, T north minus Tp So if we group the terms together, so you have, so the equation will be very similar to the previous one. So APTP will be sigma ANB TNB plus some B. Here AP will be sigma ANB, where your A east will have KR times RE delta Z by delta R. A west will have, the only difference between the Cartesian and this is you have one additional contribution from this R. So previously that value has to be constant, but here it will vary depending on your coordinate. So A north will have the KZ, and your B term is again a constant. So QE RP delta delta Z. So this is fairly straightforward. Say if you are dealing with the same thing, but now instead we have something like this. So we have discussed this previously. So if this is your R direction, instead of having a homogeneous material, say suppose you have some inhomogeneity, essentially you have two different materials. So this is of say K1, this is of K2. So this is along R direction, this is along Z direction. So I think we discussed this previously. So if you want to calculate the value of the flux at this particular phase, how do you go ahead with that? This is my P cell, This is my east cell. I want to calculate the flux at the east face. So how do I start with that? How do I get the value at this value? So the equation will be very similar. So you have K east times del T del R on the east face, but what will be the value of Ke?
It will be harmonic K1.
Yeah, but how did we arrive at that harmonic mean? So like, what is the rationale behind that?
You use a distance factor, right? Factor F, which relates the distance between the cell centroids and the location of the
Phase centroid. Okay, but the central idea behind there is your choice shouldn't affect your flux. Your flux should be same. So like,
yeah.
So if we apply the same here, the difference is like in your Cartesian system, say if this is your Cartesian system, there the idea is K east, whatever you take should be independent of this. So what I meant to say is, if you have something like this is my P cell, this is my east phase centroid, this is my capital E. So here you have something like this, some resistant kind of thing, where your resistance is from your Fourier's law. So if you have written Q as K times delta T by delta X, if delta T is your kind of potential kind of thing, so your resistance will be something like delta X by K. So from P to E you have delta X by 2K1 and this will be delta X by 2K2. So this is in series, so you have total resistance as delta X by Ke, and this is equal to K2, and from there you got expression like K equals to the harmonic mean of these two. So but when we are doing for a cylindrical coordinate system, what is the expression for the resistance we have? If you recollect from your conduction, so how is Q related to your temperature difference in say an annular cylinder? So you have something like this. So this is my R1. So this is what we are dealing with. We have an axisymmetric coordinate system. So this is R2, and if say this there is a delta T between these two, how is Q related to delta T in this particular case? If you can recollect. Delta T into, like, I'm just trying to write in the form of the voltage and current kind of stuff. Okay, so maybe you can refer later. So it will be something like ln R2 by R1 by 2 pi KL. If you can recollect from the formula. If not, you can just derive. You can recollect the formula, then fine. Otherwise, you can refer this in any of the standard textbooks for conduction. So for a cylindrical annular cylinder, this is how your delta T will be related to this. So your resistance will be something like ln R2 by R1 by 2 pi KL. So now we are dealing with cylindrical coordinate system. So if you consider the points, so now here you have a resistance which is not delta X by 2K, but then instead you have ln of R east by Rp by some, so I am just removing the constants. So this is K1, and on the other side you have ln R capital E by R little e by K2. So the overall resistance will be ln of it will be summation of these two. So instead of the direct harmonic mean, you should be using this relation to get your, like, this is my K equivalent. So you should be using this relation so that you will not violate your original condition. Like as we have seen, the flux should be same whichever way you consider. Hope this is clear. From this you can get a value expression for K is K little e in terms of K1, K2 and all your R's. you should not be using this, and instead you should be using this relation to get your equivalent conductivity and then use that in your values. The next one is in spherical coordinate systems, but this is an unsteady equation. So, okay, so there was a question on unsteady equation. I think he left the session. Okay. It is a 1D equation. So you have this set of equations. So the problem is again the same. You just have Neumann conditions on both the sides, so you will not get a unique solution. So you have to fix some reference value that for a steady state problem. But here we have a unsteady problem where your initial guess will be fixed from the initial condition will actually give that reference value, so it can proceed. So how do we start with this? I think you are already familiar with unsteady, right? Have gone through the lectures already. Hope you are. Otherwise, it is very similar to what you do previously. So now you have dou c dou t. Now previously what we were doing is just we are integrating over the entire volume. We will do the same thing. In addition, we will also integrate over the time over some delta t. So, but maybe before that I should, just for simplicity, I am just taking the r square LHS, and then maybe we will integrate. So you are dealing with spherical coordinate system, so your dV will be okay, or maybe you can directly take it in a much simpler way. We will come to that. So how do you solve this equation? Your control volume is essentially, or whatever volume you are taking is not a function of time, so you can just take this out, write it as r square c dV. So how about this equation? So this is something like your del r square d. So dV will essentially give you 4 pi r square dr, or maybe I can just simplify it even further, write it directly so that it will be easy for you. So you can write this as this dose is equals del dot d del c. So if I write in this particular way, maybe it will be easy for you. So you just apply the Gauss divergence theorem. This will be d del c dot dv. So apply the Gauss theorem. So this will be d del c dot dA. So now on the left hand side you have, I'll just take the dou dt outside. So have del t integral c dv equals, you have this d times 1 by r square del c del r into dA will be something proportional to r square times dr. Or maybe I can write it in a general form. So you have, so like previously when we have discussed, so this is your r cap direction. So if you are going in your r cap direction, what will be your unit surface area? So for a sphere, if you are integrating from one cell to the next cell, so it will be something like this. R minus delta r or if you want to say like our familiar notation, so one will be the east cell, the next one will be the west cell. So if this is my east cell, this is my west cell, so you'll get something like this. So this is very similar to the previous one. So your C here, you will take the mean value, so you have dou C. If you are taking for each cells, you have dou Cp by dou T, will be written as this, d by Re square del C del R on the east cell minus R west square del C del R on the west face. So this is again very similar. So on the east face you have yes C east minus Cp delta R Cp minus C west delta R. So maybe before doing this, okay, I don't know if you're already familiar with implicit and explicit methods. So how do you actually get these values? Is again we have two different ways. We do it either by the implicit or the explicit way. What I mean by implicit and explicit is you have something like dou Cp by dou T. You have some coefficients here. So you have some coefficient say Ap times Cp and some coefficient for east and some coefficient for the west face. So when you have something like this, the first approach is you use some say Euler method. So in Euler method, how do we proceed is we just take this dou Cp by dou T as Cp calculated at T plus delta T minus Cp evaluated at T by delta T equals this entire expression over here. So you know the initial values, C value throughout your domain, you know all the values initially at T equal to 0. So at T plus delta T, you just get this as plus delta T times this entire term over here. So you know all these values for the initial time. So at T equal to 0, what you do, your Cp at say delta T will be Cp at T equal to 0 plus your delta T times your Ap times Cp0 you know all these values, so you'll be able to calculate Cp at next time step, and then you keep on iterating. So once you get Cp at delta T, you will take the value at Cp at 2 delta T, and then so once you know this value, you Cp at 2 delta T will be essentially Cp at delta T plus delta T times and then at 3 delta T it will be dependent on 2 delta T. So you keep on iterating till your finite number of steps, till whatever is required. This is an explicit scheme, and okay, I think stability is not discussed in the lecture as of now. So this is one method. The other approach is this is forward. This is an explicit scheme, and then there is an implicit. What I mean by implicit is instead of writing dou Cp dou T as, we can write this something as T minus delta T, sorry, Cp at T minus T minus delta T by delta T. So instead of the forward step, you can take the backward step as well. So the problem here is if you try to solve this, we only know the values at the current time step or say the previous time step. So what happens is, say you want to write for say for Cp2, Cp at the next time step will be dependent on Cp1, and all your equations will be in terms of Cp2 at time t. So here on the right hand side you will be having so previously what was the case is your LHS is, this is your unknown and you know everything on the RHS, but now the case is slightly different. You have to just reverse it. So now your unknowns will be on the other hand, and like all your these values, C2 is something that you want to find, but then you don't know, without knowing this value you have to solve this equation. So this will give you an algebraic equation that you have to solve. So previously it was also an algebraic equation, but now it is implicit in the sense your unknown is currently dependent on the current time step. What I mean to say is you want to find CP at 2, but for that you need to solve, you need to know all these values which are themselves unknown. You know only the value at CP1, so at time step 1 you know all the values. You want to find the values at CP at the next time step, but in order to find this next time step you need to know the values of C east and west also, which are also unknown. So you need to write this equation for all the other cells. So you need to write for CE2, you will have some equations, and for C west also you will have some equations. Now you have to solve all of these simultaneously, only then you will be able to solve for the next time step. This is for the case of your this is what you call an implicit method. Computationally it takes more steps, but then it is more stable. So maybe I think at week 7 let's just discuss about the stability and this. So maybe we'll take this up in the next week. I think we are also running out of time. Yeah, is it clear up to this part? Stability will take up in the next week. So it's clear up to this part. Are there any doubts in this up to this?
Yeah, it is clear.
Yeah, okay. Then maybe we can conclude for this week. So next week we'll take up this and discuss the stability issues and other stuff. Thank you. Thank you for joining.
Thank you.